Good afternoon. We're going to be doing some calculations. If you have a calculator, get it ready and your clicker. I have some information for you concerning uh, the clicker participation um, data. A few of you alerted me to the fact that for some of you, the system was recording um, your participation as a zero. Not every session and not every student, but for some reason there were some students sporadically and intermittently that in the raw data file, which is what I use to create your scores that are uploaded, the data for a few students was a zero. And a few of you said, hey, Dr. B, I was actually there. I clicked and I got a check mark and I'm registered. So how come I got a zero? And I went and checked it out and I finally got an answer from the iClicker company. They had a bug in the clicker software that I was using, and they said, Dr. Brickner, upload or download the latest version and update to the new version of the software, and that'll square away all the data. It did. So I fixed all the scores, and I want to tell you about how I shipped that information into web courses and to your grades page. Because everybody's always nervous about their scores and whatnot. If you look at the grades page as of about 6 a.m. this morning, you'll see that there are two new rows. One of them is rebuild of answers, 0329, March 29th. And one is rebuild of correct, 0329. And those data, here's what it looks like right here. These data basically are counting up again your data. Now, some of you, this is not going to change because you weren't one of the students that got these mysterious zeros. But a handful of you, more than a handful, about a dozen of you, will notice in this in this row of your grades page that your clicking data is now a little bit higher. You may not have any more correct, but you'll have a few more answers. So this upper row here, rebuild of answers. And I checked it. There was about a dozen students that you'll see a change. The rest of you, you're good. Anyway, I'm not going to go back in and change each row of data in your grades page from lecture A5 all the way down to lecture A20. I could do that, yes, but it would be pretty time consuming. And this information is equivalent to that. Okay, so what we're going to do is start from this, and hopefully in the next month between now and the final exam, we won't have any more of these mysterious zeros because we have the new software version. Come on in, have a seat, any seat. Yeah, it's good. And we'll be keeping track of the data from this point. So I'm not going to erase lecture A5 through A20 because for most of you it's accurate. And this number, the two rebuild numbers will also be accurate. Well, the two rebuild numbers are accurate for everyone now. It's a difference for about a dozen of you. But from here on out, we shouldn't have any more of these zeros. And I'll still, like today's lecture A21, and maybe tomorrow night or something, I'll get around to uploading the data for it. And we'll just keep doing clicking and stuff in class. I see your question, just a second, as we go through the semester. So that's basically the announcement about that. Question in the back. What I just explained for about 10 minutes. Basically, well, just to recap, the software that I used, I downloaded at the beginning of the semester, version 7 for Mac. It had a bug in it, and that was what was giving people mysterious zeros that were here and clicked. They told me to download the new one and rebuild the grades. That's what you got here in this data. So this sum, and what I do normally is I'll sometimes update the total number of answers that you have. Okay, I guess that answers your question. All right. Also, another bit of news, clicking wise, the pointage estimate has been updated. Last time we did it was February 25th. This one I updated it as of today, so that's participation pointage estimate. And this is lectures A5 through A20. And so this will be a number between 0 and 25. Many of you have 25. A number of you have 24. Most of the class, I'd say 90% of the class has either 23, 24, 25. A few of you are low. Also, a few of you may find that your pointage is now, especially if you had trouble getting your clicker at the beginning of the semester, but you got it and it's all registered up and everything, you may find that your participation pointage is now looking sweet. 23 out of 25, 25 out of 25. And I know that's true for a handful of people in here, and hopefully that's clear to you now. Okay, so that's this participation pointage row. Question, please, or a question if you please. Okay, let's keep going. Last time we talked about this chart. Go back and take a look at this chart in your notes if you've got it. If you don't have it, you can jot it down really ultra fast. We talked about the magnitude at Earth, lowercase m, the middle column. And this is what we call the apparent magnitude. It's based on the concept that the ancient Greeks came up with, that things of the first magnitude, stars of the first magnitude were brightest, stars of higher magnitude were dimmer, and actually, as I've understood it, there are some rating systems in the world that are similar to that. Not many. Mostly the better, the higher the number. But in this one, the brighter, the lower the number, even negative, like Sirius here has an apparent magnitude of -1, approximately. Go ahead and make a note. Diamonds. If you're, apparently, they use this vocabulary anyways. A diamond of the first water is the best. That's the phrase that they use. I don't know, maybe they say that in German up there in Switzerland or something like that. But a diamond of the first water means the very best. And so, in other words, something that's got, a diamond of the second water, I guess, is nice, but not as beautiful as a diamond of the first water. So it's just one of those things you got to get used to. Low magnitude number means brighter. Higher magnitude number means dimmer. Now, the other magnitude that we use in astronomy is the absolute magnitude, and that's the apparent magnitude of the same of a star if you were at some hypothetical distance 10 parsecs. Now, right now, we're 10 parsecs away from a few stars, but most of the stars are further than that. And so, but what we do is if we can triangulate the number, or excuse me, triangulate the distance using parallax, then we can figure out the absolute magnitude because we know how far away we are. And therefore, we can figure out how dim or bright the magnitude would be if we were 10 parsecs away. And so it is an intrinsic method on the second column. This is a way of rating the intrinsic brightness of a star. This middle column, little m, is apparent brightness. It's the apparent magnitude. Capital M is the absolute magnitude, the 10 parsecs imaginary observation post magnitude. Okay, and it is a way of saying, all right, any star that you've got, pretend you're observing from 10 parsecs away. Then give me the magnitude. And that's what that column is over there. Right? And we've got different magnitudes. We talked about these last time. Here's another one we talked about, and you can jot this down if you were absent Friday, or if you left early on Friday. If a star's apparent magnitude m is, in fact, let's make this our first notes of the day because I have an explanation for this. We dismissed right at the buzzer with this question. If a star's apparent magnitude m, little m, is less than its absolute magnitude, then is it closer than 10 parsecs? Is it beyond 10 parsecs from Earth? Or is it exactly 10 parsecs? Now, that's the last clicker question I went with on Thursday last week. Here's a couple sketches. I'd like you to add this to your notes. I spent a few minutes setting these up this afternoon right before class. Here's our star. Here's this hypothetical distance where we have this hypothetical distance post. And here's a location up here, this dot between 10 parsecs and the blue star. This dot here in the upper line is closer than 10 parsecs. Okay, so we have to figure out, all right, what would be the apparent magnitude if I was here? Now here's the other example, a position of observation beyond 10 parsecs. Okay, so this would be correspond to option C, and this upper line would correspond to option A. So what we're going to do is figure out, okay, at which location does the star look brighter? And then at which location is the apparent magnitude relatively small? Okay? So it's relatively easy to figure out that if you're backed all the way up here, that star is going to be dimmer than if you were standing right here. So go ahead and make a note of that. If you're right here, this black dot on the second line, you're further away than 10 parsecs. So that star, this blue star over here, is going to look dimmer to you, either a little bit or a lot, depending on how far away you actually are, past 10 parsecs. All right. So since it's dimmer, the magnitude is going to be a bigger number. Okay. So capital M is the apparent magnitude at this specific distance. That's our distance standard. Right. Pretend you're at 10 parsecs, then rate the apparent magnitude and give it the symbol capital M for absolute magnitude. And then down here, just observe it from out here. It's got to be a larger apparent magnitude, little m. Okay? So that's this one. All right? But the question itself says m is less, little m is less. So it's got to be this one up here. So make a note for this one. If you're in here on the upper line and you're between that 10 parsec hypothetical observation post and the star itself, you're in here, I don't know, that's at about 6 parsecs, I guess. 6.1, I don't know, whatever it happens to be. That's going to be quite a bit brighter. Okay, so whatever capital M is, if you're right here, your apparent magnitude is going to be below that, smaller than capital M. So if you have an absolute magnitude, capital M here, and go ahead and make a note of this. And I didn't put it in the diagram, but you can add it to your sketch. For instance, say that the absolute magnitude, capital M, at 10 parsecs is 1, 1.00, just, for a round number. For example, now we got a star, you're 10 parsecs away from it, it looks like magnitude 1. That's a pretty good bright star, okay? Out here, on the lower line, the distant observation past 10 parsecs, little m is going to be larger than 1. So it might be m equals 2. Little m equals 2 over here. So make a note of that. Little m would be equal to 2. Right? Over here, for instance. And little m over here, if you're in between 10 parsecs and the star, you've scooted in a little bit, you're going to say, whoa, my apparent magnitude is 0.2 maybe, right? Something less than 1. So make a note of that. That's what you're going to observe in this kind of a situation. And that makes this option A the correct answer. Now, the reason I went through this is because I want you to grab and kind of hold this magnitude concept. It is tricky even for me. I always have to, think whenever I'm working with magnitudes and stuff, I always have to think, okay, small magnitude brighter, big magnitude dimmer. Okay, so I have to think that, and so it's just one of those things that you just gotta kind of get used to. Okay, kind of like, like in England they drive on the other side of the road, the left side of the road, and we drive on the right side of the road. It's kind of like that. So you just got to get used to it. Okay, now I want to give you a little bit more instruction about magnitude system. And here's how it works. The magnitude system is actually a logarithm of two brightnesses. And the brightness, capital B, of the star that you're looking at, divided by the brightness, capital B, of Vega. Okay? And then you take the logarithm of that. Now, we're not allowed to do logarithms in this class, but for those of you that have had trig or calculus, or maybe algebra, I guess, you've met logarithms. Yeah, they're in here, and this is one of the reasons it's kind of a, I don't know, tricky rating system to handle. So don't worry about calculating logarithms. We're not going to be doing it. Just saying, yeah, they're in there, Sarah, and you can deal with them as you like. We won't be calculating with them, but they're in there. All right. Now, here's the magnitude scale. Go ahead and draw a horizontal line and just give it, I don't know, -6 to +6. Vega's right in the middle. Vega's our 0 point. We define the Greeks didn't think about magnitude 0. They thought about magnitude 1. But we're kind of pulling a fast one on the Greeks. And it's kind of like the difference between Celsius and Kelvin scale. We're kind of shifting the 0 point a little bit. We're shifting it to Vega. And if you're up here in the positive m's, that means that from Earth, you are dimmer than Vega. So like right here where my cursor is, I'm at magnitude little m equals 4. Okay, that means, and there's plenty of stars that we see every night, if it's a clear night. By the way, has anybody looked at the nights under the stars today? Nobody's done it? Okay. Hopefully you guys will be able to go this week, but it's going to get worse and worse. We're getting a lot more rain. The weather pattern is getting wet, so it's possible we might not have any more nights. But we did have a good bunch, and I know a lot of you got them. Now, over here on the dim end of the scale, +6 and so forth, theoretically, magnitude 6 is the dimmest star that you can see with the unaided eye. So maybe Chuck Norris can see magnitude 7 or so, I don't know, but for most normal human beings, it's right about here. Okay. Now, over here on the negative side of the scale, this means if you have a negative number for the apparent magnitude, Sirius should be over here. There's Sirius. Okay, Sirius has got a, from Earth, Sirius has got a negative magnitude. Okay, negative 1 point something. All right, now, go ahead and jot that in. And we're going to be working with magnitudes and luminosities here for the next week or so as we try to figure out different patterns, Leland, in the stars themselves, and looking and measuring at as many stars as our eyes, as many stars as our telescopes, as many stars as our spacecraft can get us, the distance and the brightness. Let's do another calculation here. Actually, not a calculation, but a question. And it's related to this table. And you have, if you haven't jotted down that table of Polaris and everything, here's a chance to copy in some more lines. Question 2. This star is brighter than the others if viewed from Earth. Actually, I think this is question 1 for today. Which of these stars, A, B, C, or D? Which one's brighter if viewed from Earth? And you know what you should do? Write down that question and then your answer. And around this, the clause, if viewed from Earth, circle that or, put stars next to it or something. That's the key phrase. When you're reading a test, and I always tell you, read carefully. Don't go too fast. Read very carefully. That's the key phrase that helps you figure out the answer. Now, brighter means further into the negatives or a lower positive number, right? And if viewed from Earth means look at this column over here. So let me close the question. So what we're looking at is this column here, and we're looking for the number here that is the smallest number that's positive, or maybe even a negative number. And that happens to be Vega. So this is the correct answer for this question. Let's see what you guys did. Yeah, a lot of you got it. That's good. All right, now I got another question for you. Okay, here it is. This star, same bunch, same data, same table. This star is intrinsically brighter than the others. The same set of 4 stars. Which one is intrinsically brighter? And in this one, if you want to write the question down and then emphasize it. Matter of fact, I'm going over this with you so that you can write it in your notebook and have it ready for studying for exam 3. Hint, hint. You'll be ready. You have it. And the key phrase here, the kicker, is intrinsically brighter in this one. That tells you which column to look at. And then magnitude, data itself tells you, to look for the smallest number. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys got here. Yeah, you're doing good, Antares. And if you're wondering why, on this one, intrinsically brighter means look at the capital M absolute magnitude column. And then in that column, look for the number that's either the lowest positive number or the deepest into the negatives. And that happens to be Antares. Whoa, -5. That's almost as bright as Venus. Or that's about the same brightness as Venus. So, or Venus at its full phase. So if we were, and this is 10 parsecs away, we're not even a 100th of a parsec away from Venus. You're a few light seconds away from Venus. This is, many, many, many hundreds of light seconds away, and it's still brighter than as bright as Venus. So it's a pretty bright star. So, and final comment on this, add this phrase as well. And this kind of amplifies the concept of intrinsic. You can say that this star is brighter no matter where you view it. If you're 10 parsecs, if you're 100 parsecs, if you're 153.7 parsecs from every one of these stars, Antares is still going to be the brightest. And that's what it tells you. So if you get close in, 1 light year from all 4 of those stars, Antares is still the brightest. It's going to be blazing. If you're 1 light year away, that's going to be, woo, it's going to be a hot one. You might even get sunburned from another star if you're that far away. Now, fancy, fancy, fancy stuff. Vocabulary term, distance modulus. Little m minus big M. That's a fancy astronomy term. Bunch of egghead astronomers decide to take the difference, and little m and capital M are both logarithms. And so when you take the difference of 2 logarithms, you may remember, that's equivalent to something. And I'm not going to go into exactly what it's equivalent to, but subtracting logarithms is a thing. And anyways, distance modulus, it is a numeric way with fairly small numbers of expressing the distance. So one way of expressing the distance is parsecs. Another is light years. And a third way is distance modulus. And the advantage of distance modulus is that the numbers don't get gigantic. Okay, light years and parsecs, you can be up in the megaparsecs, if you're looking at another galaxy easily. But distance modulus is a little bit easier to work with. So astronomers use that. You'll see it in your readings and stuff here and there. And it's another one. We're not going to really work too much with distance modulus, but that's what it is. Yeah. Now, let's talk about spectra. Big, 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 big topic in chapter 12. This is table 12.1. And astronomers have been looking at spectra since the late 1800s. Okay, they used first black and white film, and then eventually color film. But I think probably black and white is all you really need. You have a very good diffraction grating, and you see, the light from the star disperse into a diffraction pattern, and you can start, if you do enough stars. In the 1800s, they started to see patterns. Initially, they set up a spectral typing system using capital letters from A through Z, but then they thought, there's a lot of letters we're not really using that much. There's only a few stars, and most of the stars are in this set of categories here: O, B, A, F, G, K, and N. And the first is letter O if you orient it by surface temperature. But letter O, I don't know what is letter O. That's the 15th letter, I think. Okay, so the letter O was the 15th class that they set up. But after they figured out in around 1900 the correlation between surface temperature and color, they were able to say, hey, whoa, this is not really the 15th. This is actually the hottest of all the stars in these big spectral types. So most stars that we see fall into those 7 types: O, B, A, F, G, K, M. The other letters are not used very much. In fact, I think some of them probably aren't used at all. I've seen type R and type T. I've seen type P stars. They're exotic, unusual stars. So nothing, really well, I guess there's guys that, you know, study them and stuff. But most of the astronomers are focused on this series of spectral types. Now, table 12.1, go ahead and make a note of that, table 12.1. Make sure you read that in your textbook, the paragraphs and pages around that. Um, Here's a blow up of it, and it shows the different spectral types. And the surface temperature is listed here in the third column, and some examples are in the second column. So stars of Orion's belt, Rigel, Sirius itself, Polaris, the Sun and Alpha Centauri. The Sun is a G2. And the spectral types have been subdivided into different numeric ratings. Arcturus is a red star. Betelgeuse or Proxima Centauri. Betelgeuse is a giant star, and it's red. Surface temperature is a little bit less than 3,500. Proxima Centauri, also known as Alpha Centauri C, that's the actual part of the Alpha Centauri group that's right now closest to Earth. That's also red, surface temperature about 3,500. And you can see where over here the absorption features, in other words, these gaps in the colors, the rainbow has got gaps. That means absorption features. Some of them are really bright emission lines, and you can see those as well. So you can see emission lines down here for relatively cool stars. Up here for hotter ones, you can see absorption lines. And different different spectral type means you have different absorption features. Here's the hydrogen lines. Here's H alpha all the way down here. And then once you get down to G, K, and M, you don't really see any absorption features for that spectral line of hydrogen. Same thing over here with H beta and H gamma, right? The first four spectral types, you'll see some absorption features, but not really that much going on down here. Now, over here you see calcium, titanium oxide. These are actually molecules. Titanium oxide over here, two different groups of lines. Yeah, so spectral types, definitely spend some time looking this over, looking at the different wavelengths that are brightest, and the description of the features, like type M, strong molecular lines. And make a side note, type M, side note. Many, it should be capital M for many, because many small red stars are type M. Zillions of them. They're tiny, they're numerous. There's plenty of the other ones, but the most numerous, we think, is type M. They tend to be fairly small, except for the giants. There's not many giant stars that are type M, relatively small number of those. They're much bigger and brighter. And you may say to yourself, hey, Dr. B, how do you know that they're bigger? I will tell you how to figure that out today. How to distinguish between a small red star, like Proxima Centauri, and a giant red star, like Betelgeuse, in the constellation Orion. Another thing that the spectra can tell you is the Doppler shift. And this is, my outline is incorrect. It's not figure 11.8, it's figure 12.7. This is the previous edition. I copied this set of notes here from a previous year when the textbook was numbered differently. Anyways, figure 12.7 is the figure that we're talking about here. And it shows two stars orbiting each other, or this blue star orbiting this big red star, A. Right? And it shows the spectra that you observe on Earth for two different parts of its orbit. Now, over here, go ahead and draw a circle around star A. and put a smaller circle for star B down here, and a small circle up here for star B, right? And make a note that this one's going clockwise. Now, not all the stars are going clockwise when viewed from Earth. Some are going the other way. Okay, some are, they're all at different tilt angles. So this was kind of an idealized view of a star that we're looking straight down, even with the plane. So we're looking at the star on its orbital plane is around the big stars, just like this, and we're looking straight at it. So we see it on the left, down here, this lower point, it's moving away. So make a note, down here, the star is moving away from Earth. Up here, for just a short time, it's moving straight toward Earth. Now we can pick that up. The way that we pick that up is the Doppler effect. The Doppler effect, it affects light as well as sound. There's a Doppler effect for sound. You may have heard it when you hear a train approaching, and it seems to have a high, the train whistle has a high note, and then as soon as it passes you, it kind of dips down to a slightly lower pitch. You've probably all heard it. Police sirens, ambulance siren, fire engine. You hear it. When they go past you, you sometimes hear it. The Doppler effect. And here's what it looks like. Here's the H alpha line. All right. Now, when the star is moving toward Earth, they measure the H alpha line right here. But when it's moving away from Earth, they measure the H alpha line down here, a little deeper into the reds. And in the lab, the H alpha line is supposed to be right here. All right? So when the star is moving toward you, okay, up here, toward you, the wavelength is shifted to the blue end of the spectrum. And that's why we call it a blue shift, right? The Doppler blue shift, okay? If it were sound waves, that would be higher pitch as a train comes toward you, or as the ambulance comes toward you. And now down here, the shift is deeper into the reds. This is called a red shift. When you look at the spectrum of a star that's moving away from you, you can see H alpha as an absorption or emission feature, but it's shifted just a little bit. It looks a little redder than usual. Go ahead and make a note of that. Red shift means H alpha looks redder than usual, deeper into the reds. And if you measure the wavelength, it's a little bit longer wavelength. And go ahead and add to your notes up here, in a blue shift, it means the H alpha line, whoa, it's a little more orangey than usual. And it's, sometimes we see the H alpha line shifted into the yellows, for something that's really booking away from us. Right? So you can get a blue shift or a red shift, various magnitudes. Most of the time it's pretty small, but if we have a good telescope and stuff, we can measure it. And sometimes that's all we see. The only thing, we can't see left and right, but we can see red shift and blue shift, right? And from that, so we can figure out a velocity. Now this, don't worry about copying this, but do take a look. From looking at the red shift and blue shift, you can compute a speed, v, in kilometers per second. And so with that, we can figure out, a lot of times, how heavy the star is, how many kilograms of mass it has, by using Kepler's third law. Okay? And so right here, we have a very big radial velocity. That means it's moving away from us. V subscript r means radial velocity. And here it's, I don't know, it's about 40-something, 50 almost. That means it's moving away from us. And then over here, we have a negative, about a negative 10 over here, that means it's moving toward us at this part of its orbit. And then it's back up here to about 50 over here. And then here's the other star with the black, with the open squares. Okay? And astronomers try to get these light curves like this, or these aren't light curves, sorry. These are Doppler shift curves, or velocity curves we would call them, and figure out, okay, these two stars, they're orbiting each other. We can't make them out, but we can see that they're there. This is two things, because this one's moving toward Earth when this one's moving away from Earth, right? And vice versa. This one's moving away from Earth, the open squares, when this one's moving toward the Earth. So that means they're orbiting each other, mutual orbit, mutual gravitational interaction, and we can deduce a lot from that. That's called a spectroscopic binary. You can't make out its orbit visually, but you can see the spectroscopic red and blue shift. Right? So spectroscopic binaries. We've talked about this one before, Ursa Major. Alcor, Mizar A and Mizar B. You can resolve Mizar A and B visually, but you can't get the two stars hidden in this blur of light and the two stars hidden in this one. You have to get them spectroscopically resolved with a velocity curve like the previous slide. So we can break that stuff out. So the Doppler shift, the change in pitch of sound, the change in color of light, allows us to figure out, whoa, we got two stars orbiting each other. Or, sometimes we can just tell, it's constantly blue shifted, so that means it's not orbiting some other star, but it is coming toward Earth. Okay, so, or if a redshift, it's moving away from Earth. Matter of fact, you've all heard that phrase, the Big Bang Theory. The Big Bang Theory is that the universe began with a ginormous explosion, and that eventually galaxies formed, and all the galaxies kept, moving away from each other like smithereens, moving away from an explosion, a Big Bang. And the reason that we figured out the Big Bang Theory is by looking at galaxies. And almost all the galaxies have a big redshift. In H alpha, H beta, any line that we can see, all the lines are redshifted, except for a few, the ones that are close, like Andromeda and stuff. But anything past Andromeda, they're all redshifted away. So we know that all the galaxies are moving away from us. The universe itself is expanding. And that's how we know it, by looking at redshift. Okay, some more in depth about spectral features. We know how to look for absorption features and emission features. The absorption features are these big dips where I have the arrows. Emission features are where you have a dip upward above the general curve. And this is a diagram of some absorption features for a star in the orange range. Fine-tuning, OBAF, GKM. The spectral types, the standard set of 7, each one's subdivided into 10 subdivisions, 0 through 9. Okay, so G0, G1, G2, G3, on up to G9. And then K0, K1, K2, And the sun is a G2. Alpha Centauri A and B, they're G2s. So we think that they're cousins, distant cousins. One's you're from Florida, and one's your cousin in Tennessee. It's Alpha Centauri. So the same DNA and same looks. Sun, Alpha Centauri, A and B are G2s. Sirius is an A1. So Sirius is up here in the hot end, up here, and it's in the second category. It's an A1. It's not an A0. It's an A1. Alpha Centauri C, red M5.5. Yeah, you can get decimal fractions. I think most of the time it's either a whole number or something 0.5. And we're going to be doing just a little heads up to you for Thursday. I'm going to be handing out your graphing assignment. Um, I could be giving you handouts and some instructions on Thursday in how to start it. It's going to take you some time to do it, and I'll grade it when you turn them in. You'll have plenty of time to do it, like a week or so. But you'll be working with some of these spectral types, like 5.5, A, A1.5, stuff like that. So the spectral types, as I've described them here, even subdivided into 10 subdivisions, they're very helpful, and we now know that the spectral types, the original ordering A, B, C, and on up to Z was okay, but in terms of physics and thermodynamics especially, we now know that the proper ordering from hottest surface temperature to coolest is OBAFGKM. And again, it shows you, that, as I like to emphasize, that, and I think a lot of the greatest scientists exemplified is that when you're studying the universe, whether you're studying atoms or galaxies, it behooves you to be humble about what you observe and what you're studying, because I guarantee you don't know it all. And it's very common for a scientist to say, boy, the more I learn, the more I realize how much I don't know. Sir Isaac Newton was famous for saying that, Einstein as well, Michael Faraday, all the really great ones. A lot of I'm not going to mention any names, but there's a lot of guys in the United States right now, Europe, that are very talkative and not very humble. And even though they have a lot to be humble about, and they should be humble, and the best scientists are humble, and so we'll be compassionate to the people that first started A through Z with the spectral types, and later figured out it's OBA, much better, FGKM, much better. And here's your and this is from the previous version. Table 11.1, it's now 12.1. The sun is right in here. Emphasize that, the G type. Zillions and zillions of stars are type Gs. We see them all of the time. Lots of M's, lots of K's, lots of G's. Hotter than G, though, it's a little bit more rare, right? Type O and B, fairly rare. We see them, they're there, there's lots of them, but compared to the G's, the K's, and the M's, not so rare. Now, let's get back to distances and magnitudes. If you know the apparent magnitude, and if you can triangulate the distance, then you can figure out absolute magnitude, or total luminosity, capital L, right? Because if you know the distance, Jacori, and the apparent magnitude, you can say, all right, I know how far it actually is, and I know how bright it is from Earth. So if I use the inverse square law and everything, I can figure out how far it is if I was 10 parsecs away. And that's your capital M. That's your absolute magnitude. Matter of fact, you can also use it to figure out, how many watts per square meter the surface is going. The way you get that is just look at the temperature. Now, I'm going to do some calculations here in a minute. So get ready to hold on to your hat. This is a section. This is actually from chapter 5. So dip back to chapter 5 to look at this, figure 511. This is called Wien's law, W-I-E-N apostrophe S, Wien's law. This is it. The maximum wavelength in a black body spectrum times the temperature is equal to this constant. I don't know how he figured it out, but I guess if you look at enough, you measure enough black bodies in the lab and their maximum wavelength and their color, you can figure it out, right? So every object emits thermal radiation, right? You emit a lot of IR. That's why the U.S. Army can keep an eye on you at night, track you down like Chinatown by using infrared goggles, infrared optics, okay, because you emit a lot of IR. Now, a stove that's really hot will emit a lot of infrared, also a lot of red, but not a lot of the other colors. I hope not. I mean, you can get a stove really, really hot, so it looks, blue hot, but boy, most of the time, a really hot stove at home with the burners on, the electric burners anyways, is going to be red. And so just write down, et cetera, et cetera. So no matter what the temperature is, if you can spot the maximum intensity color, you can figure out the temperature. The peak of the spectrum depends on the temperature, and this is the law for it. So make sure you write that down. The peak of the spectrum is, in terms of wavelength, lambda max. The wavelength at the very top of this bump. So this is a bump here, this blue one, for a hypothetical 15,000 Kelvin star, really hot. Now, a real star would have all kinds of dips in it from absorption features and maybe some emission features. Okay, so this one's kind of hypothetical. A perfectly smooth 15,000 Kelvin star would look like that. Now, here's Roy G. Biv right over here. This second curve in figure 511 is for the sun at about 5,800 Kelvin. All right, and that peaks right in here in the green. Matter of fact, let me go to the next picture. Here's the same formula in case you were jotting it down. And you're going to need to jot it down because you're going to do a calculation in just a minute. Okay, so make sure you have it written down, Wien's law. Here's the peak of 15,000 Kelvin star, really hot. Okay, and this one, it's not even in the visible, it's in the shorter wavelength. This is out here in ultraviolet. So this one, so make a note, 15,000 Kelvin, peak wavelength, ultraviolet. Okay, so it might be, I don't know, maybe about 150 nanometers. Okay, small wavelength, high frequency, ultraviolet. Right, this one, okay, there's the sun. And our peak, our lambda max is actually in the green. So the sun theoretically is a green star. We see it as a white object, kind of yellowish, if we're in the atmosphere of Earth. But sunlight, if you put it through a prism, it breaks up into all the colors, and the hottest color or the most energy is coming through the green. There's another star. 3,000 Kelvin. This is a red one. And your peak here, now this one peaks outside of Roy G. Biv on the other side. So this one would be an infrared peak. It's pretty cool. Man, let me say that again. The surface is fairly cool compared to Earth. This one is modeled at 3,000 Kelvin. Right? We see a lot of stars like that. And side note, the cooler the temperature of the surface, the less energy. In other words, the shorter the overall curve is. Now here's you down here, 310 Kelvin human. You're not putting out much energy. Okay, so this is just a little teeny blip down here compared to this guy. This guy's blazing up here. His peak is way up here in 10 to the 8th. Whoa. Right? But here's you. Okay, 310 Kelvin, normal human being. And yeah, you're emitting a lot of infrared. And we know exactly the heaviest band of infrared for humans. So that's how we design night vision goggles. Now, we're going to use this formula. I hope you've got it written down. We're going to calculate some temperatures. Okay? Get your calculator out and your clicker, and let's try it. Here we go. Multiple choice. 5,700 nanometers. Now, according to NASA, that's the middle of the yellows. So what's the surface temperature? Use this equation. So put in 5,700 nanometers here and figure out T. Do a little bit of algebra. I'll give you a minute. And we'll go over the method for doing this after the question. So if you get stumped, just try your best. I might give you some calculations like this in web courses. I don't know if I have any back there. But A, B, C, D, or E. Now these numbers are all 4,000, high 4,000s and on up to the high 5,000s. So these are temperatures. These are temperatures of the surface of many stars. And definitely consult with your neighbor if you need to. Don't feel like you have to stay quiet. I expect you to talk and kibitz and everything. If you want. One minute. And actually what you can do is try out all 5 of these numbers with 570 times 10 to the minus 9 on your calculators. See which one gives you 0.002898. That would work. But I'll show you a way to calculate it directly in about 30 seconds. Fifteen seconds. Make a decision. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, see what you guys got here. Yeah, we got it. That's all right. We have a spread in the answers here. So a lot of you voted for C, but a good fraction voted for A, B, D, and E. Only 2 people voted for D. Let's see what we got here. Here's the correct answer, and I know a bunch of you, the majority of you voted for that. That's good. But let's go over the method for calculating it. Here's how you do it. You take that constant and you divide by 570 nanometers. Right? Go ahead and jot this down. You're going to want to know how to do this. At some point in the future, hint, hint, even though I can't tell you what's going to be on the exam, and I tell you to use your lecture notes as your study guide, I can tell you that it'll be very good if you can remember how to do this. All right. How you do it on a calculator, you do this, you'd put in 0.0002898, that's the numerator, and then the divide by sign, and then here you'd put in 570 EE minus 9. at least on my calculator, I have a little Texas Instrument. It has an EE button. You might have something else. I don't know. You have to figure out, you got to use scientific notation carefully in this part of the course. All right. So there's how you start. Now, here's how I would do it. I mean, I would change, if you're doing it on pencil and paper, I would change this 10 to the minus 9 and I'd bump it upstairs. You can always do that. If there's a 10 to the minus 9, Charles, in the denominator, you can definitely write it as a 10 to the regular 9 in the numerator. Perfectly kosher. Right? And that makes things a little bit easier. Then you divide these two numbers and you get something times 10 to the 9th power. All right? And I forgot to put in the, oh, here it is, K. Notice that meters cancels meters here. Okay. So now I'll only have Ks, kelvins. And so here's what you get. Okay. 0.002898 divided by 570 is this junk. Whoa. 5 zeros. 0.0000000500842 times 10 to the 9 Kelvin. Now that's all right, but wouldn't it be nice to actually have a regular number instead of 0.00 blah blah blah? Right, so here's how you figure that out. This is going to be a few thousand, because all the answers in the multiple choice were in the somewhere between 4,000 and 6,000. And it's kind of hard to tell what this would be. So what you do is you take the decimal point and you jump it 9 places to the right. All right, so here we go. 1, 2, 3, whoop. A little bit too fast for me. Anyways, that's 9. So go ahead and jot that down. All right. So the decimal point goes right after the 4. Now you still have a 0.2, but now you have 5084.2. And that is the answer. 5084 Kelvin. Now I'm going to give you another one. So make sure you ask me a question. Go ahead. Kyrell, right? Yes. Good. So do you jump the decimal for any amount of? Yeah, until I can get, it was multiple choice. I was in the thousands. So, and what that does is it takes this out, gives me just K's, and it puts me in the thousands and at 0.2. All right, so if you don't, if your answers are in a whole number, jump it 9 times to the right. All right. Another question, because you got a very similar calculation to do next. See if we can get 100% on this. So nobody's asking me a question. That means you guys are going to lock it in. You're locked and loaded. All right, let's see what you guys can do. Here we go. Star shows a spectrum peak at 501.6 nanometers. Give me the temperature. And this one has 5 temperatures for your temperature convenience. And just do it the same way we did the last one, either on paper or with your calculator. And hopefully, if you guys can crush this, crush it like a bug, then I might let you dismiss early. You think? But if you're, if you're distracting yourself by thinking about a plate of shrimp or something like that, don't do that. Focus on wavelengths. Come on. I can never forget the time you got so ticked off when I said that. it's a famous line. It does exactly. It's exactly right. It's a famous line from a movie about total nonsense called Repo Man. Yeah, with no, not Charlie Sheen, but Charlie Sheen's brother, Emilio Estevez. It's very funny. Very funny. 20 seconds. Can you do it? Can you work it? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching! You're not dismissed yet. Hold on. What you just figured out is the temperature of our star, the sun. Now, jot down these last concepts, and then we'll dismiss. If you know the temperature, you can calculate how many photons per second per square meter. So every square meter is going to be spurting out so many photons per second. If you know how many photons per second per square meter and the luminosity, you can figure out how many square meters of surface. If you know how many square meters of surface, you can figure out the radius. Because the area of a sphere is 4 pi r squared. So if you know the area, you can figure out r. Figure out r squared and then r. So my wonderful students, this is why we want to always get parallax. All right, you're dismissed. Homework in masteringastronomy.com. Not a big one, but go and look a little bit later tonight. See you on Thursday.